understand that it's...
Good morning.
Good morning.
Good morning.
Welcome to the second half of quantum theory. We'll focus on relativistic quantum theory or quantum field theory for the next 2 weeks. I'm Dan. Please call me Dan. And my office is just down the hall. All the other academic staff, academic programs admin. So I have some listed office hours on the Google Calendar. Please don't limit yourself to those office hours. That's just if you want to know ahead of time that I'll be in my office. If you drop by, chances are very good I'll be in my office. It won't be 100%, but please do stop by outside of those times. If you don't find me or it's after hours, please feel free to send me an email. So I encourage all of you to ask lots of questions during lecture. If for any reason you don't feel comfortable asking questions in person, you can ask me after lecture. There's also an option, ask anonymous questions during lecture. You go to this website, Slido, and type in this information. You will be able to ask questions. It'll show up on the back screen there. You don't need to enter your name. You can make it non-anonymous, but don't enter any identifying information, and it'll just show up back there. I can address the question. So please, whatever way is most comfortable for you, but don't hesitate to ask your questions. Comment about the course website. So you've all been using the course website for Bindia's half of the course. My half of the course has many quizzes. Those are intended for you to engage with the material and check your understanding. The intention is you do them in the order that they show up. So I have a lecture and then a set of quizzes, then the next lecture, and perhaps a tutorial. Some of the quiz questions ask you to do short derivations. Those quiz questions will, yes, if you, so yes, there's a question at the back. A little hard to read, but I can see there's something. Just a smiley face. Some of the quiz questions. Sorry, Ellie?
Sorry?
You said something?
No, I was
Oh. Some of the quiz questions ask you to do short derivations. These are derivations that aren't so that if you do have any issues, you can come discuss with us. But they're less interesting derivations than the ones that we'll do in tutorial. Less physical concepts going on, but they should be calculations that are doable in a few minutes. And if you do have any issues with those, please come see me or Caroline. Also, the interview questions have already been posted. Posted at the beginning of the course. I don't anticipate any changes to those questions for my half of the course, but there may be. I might slightly tweak them. I'll let you know if that happens, and I will do that in the near future. Before we get started on the content, any question on anything organizational? Okay, so concretely, the question we are going to address in the next 2 weeks is what happens if we send a set of incoming particles at each other. So they collide. And after the collision, we have some outgoing particles. So our goal is going to be to describe this process, collision. If we specify the type and momentum of some initial incoming particles, can we predict what's going to happen afterwards? Very concrete question, and we'll focus on this question for the next 2 weeks. Many of the techniques we'll develop will have other applications, but for concreteness, this is the question I'm going to focus on. And in a number of limits, this is a question you already know how to address. So, particular, if the particles or objects in this collision are slow and large, we can use Newtonian mechanics to describe this collision process. So this is something you learned in one of your first physics classes. If the particles are moving fast, but they're still large enough that we don't need to use quantum mechanics, then this is a relativistic collision problem. You also know how to address. We can solve this using special relativity. On the other hand, if the objects are small and slow, this is a quantum mechanics scattering problem. And also a question that you have the tools to address. You can use the quantum mechanics you know to describe this process. So we're going to focus on this last quadrant here. So this is where quantum field theory lives. And there are going to be some new features we will see when we are dealing with objects that are both fast enough that special relativity is important and small enough that quantum mechanics is important. And one of the most important features we'll see that is present in this corner of this chart, it's not present in the other corners, is we can have particle creation or annihilation. So if you notice in this diagram, I have 2 particles coming in and 3 particles going out. It's not an accident. That's one of the key features we'll be focusing on. So we can have particle creation and annihilation. And in a few moments, I'll give you some reasons why you might expect that when both quantum mechanics and special relativity are important, you might expect that particle number is no longer conserved. So I'll go through that in a few minutes. But before I do that, I just want to spend a few minutes talking about units. So throughout this course, we're going to use a system of units known as natural units. So we're dealing with quantum mechanics, and basically nearly every formula we'll deal with in this entire course will have an h-bar in it. We're also dealing with special relativity, and we're going to focus on the case where things are moving close to the speed of light. So most of our formulas will also have a c in it. And to simplify our formulas, and also to simplify some of the dimensional analysis that we'll do near the end of the course, we're going to use a system of units where h bar and c are both 1. This is very common in quantum field theory. Occasionally, I'll restore units to point out the dependence on h bar or c when that's interesting. But for many parts of the course, the h bar and c dependence won't be a key feature that we'll be focusing on. So to save us a lot of algebra and also to simplify our dimensional analysis, we use this set of units. And in this set of units, there's only one dimension of full quantity left, which we'll take to be mass. And we can write the mass dimension, of a quantity like this with square brackets. This means the mass dimension. And this formula means that a mass is equal to a mass to the first power. This indicates the exponent of m. And we can express any quantity once we set h bar and c to 1, is some power of mass. So one example is energy. Can anyone tell me what the mass dimension of energy is? Yes, Rokas?
1.
1. Why?
Because it's mc squared.
Exactly, yes. The mass dimension of E is 1 because E equals mc squared, and C is 1. They have the same units. Similarly, energy, the mass dimension of momentum is 1. We can write, there's any number of formulas we could use to write this, but we could write dimensionally correct formula is E is equal to P squared over M, or 2M. So it should have, P squared should have the same units as E times M, both of which have units. Mass dimension 1. So energy and momentum and mass all have the same units. If we're dealing with a high energy particle, it also has large momentum. And position and length have the same units because, position and time have the same units. We can relate them by a factor of c, x equals ct. And can anyone tell me what the mass dimension of position is? Sasha?
-1.
-1. Why? Good. Why?
Well, it's like you could think of I don't know, you can relate it to velocity, I guess, and the units cancel out for velocity. No, that doesn't tell you why. Dang it, I'm just too used to it and I don't remember.
Okay. Yeah, Robin?
Commutation relations.
Commutation relations. Yes, that's a good way to see it. Thank you. There's many right answers, and thank you, Batcha, for a partial answer, and thank you, Robin, for your answer as well. Yeah, so this says mass dimension -1, say, because x p h bar. Okay, so that's just an aside, and many of the formulas I'm going to write very shortly and throughout the course. We'll be missing h bars and c's, and that's why. And we'll use this dimensional analysis more near the end of the course. So that will be relevant later part of the course. Any questions on this? Okay, there's a quiz on this so you can check your understanding later as well. Okay. So I claimed a key feature quantum field theory is particle creation and annihilation. So let me just give you a extremely crude argument about why you might expect this. We'll be more careful later, but just give you some motivation for why we might expect this. Let's imagine we've got a particle in a box. And let's say this box is a cube of size L. And so if we put a particle in a box, then the uncertainty principle tells us that there's an uncertainty in the momentum of the particle, which is like 1 over L. That comes from quantum mechanics. And special relativity tells us that energy and momentum are about the same thing, at least if the momentum is large. And we also know, based on Einstein's famous formula, E equals mc squared, that mass energy is a form of energy. Convert other forms of energy into mass. So combining these relations tells us if we make the size of the box small enough, then maybe we don't actually know how many, there's some small enough so that the uncertainty in the energy is bigger than about 2m. Well, it's not clear, at least from this argument, that there couldn't be another particle in the box. It couldn't have two particles. So is it one particle or two? And this argument is crude enough that I can't give you a real answer to this question. We'd have to think about how the particle is interacting with the box. Might do some more careful. But this suggests that if we combine quantum mechanics, special relativity, well, at least it's not unreasonable for particles to be created or destroyed. And we'll be much more careful and explicit later. Yes, Mary.
Sorry, how can energy be approximately momentum and equal to mass if momentum is much larger than mass?
Okay, so yes. So energy, if E squared is P squared plus M squared, so if E is much larger than P, then these should be approximately the same. Yes, so that energy can be converted into mass is what this, maybe I should use a different, I'm being crude here, very crude. Yeah, so there should be corrections to all of these formulas. I'm really just trying to do some dimensional analysis. You're right that I can't simultaneously use both these formulas. Yeah. So I'm just writing this formula. Say dimensionally, momentum and energy are the same thing. Energy and mass are the same thing. They can be other types of energy can be converted into mass energy. So please don't think of this as a derivation. This is very crude dimensional analysis. Okay. Yes, do it.
I think this might be wrong, but a possible fix to that might be, instead of starting with delta P delta X equals H bar, H bar, maybe we can start with delta E delta T is like that, and then delta T is like delta X because the speed of light is 1, and then so on.
Yes, I think that could work. I would do it. Yes, so there are ways we could try to improve this, like the ones you suggested, other ways, but we'll look at other systems where we can very explicitly see that the particles are created or destroyed. This is really just meant to be some motivation. I've not been careful at all, not even pretending to. Okay, so in the bottom right corner of that chart up there, I said that if we have fast, small particles, we're using quantum field theory. One question you may have is, why do we need fields? After all, our goal is to describe the scattering of particles. And there's a number of answers to this question. And let me just give you a brief overview of some of the answers. In quantum field theory, the quantum field theory 1 course, starting in a few weeks, you'll look at this question in much more detail. But I just want to give you some feeling and some overview. And so one answer to this question, why fields, is fields are a way to implement locality. In classical physics, one motivation for why we introduce fields is to prevent action at a distance. We have two electric charges. Charge A doesn't instantaneously emit or cause charge B to move. Instead, both charge A and charge B affect and are affected by an electromagnetic field, and that's how they influence each other indirectly through local interactions with a field. So fields implement locality in classical physics. A claim is that it's at least reasonable to expect they do the same thing in quantum physics. This is a question you'll look at more in quantum field theory 1. And so what you'll do in quantum field theory 1 is you'll show that, or argue that quantum mechanics plus special relativity plus locality more or less, not quite a proof, but there's some fairly strong arguments you can show that if you want to have a theory that respects these things, it at least has to look something like quantum field theory. They'll do this in quantum field theory 1. This part. And if you have a quantum field theory, you can take a classical limit and get a classical field theory. One way we can think about a classical limit is taking the limit h bar to 0. Not dimensionally correct, but it's a useful way to think about it. Or take the limit to the limit to the action divided by h bar goes to infinity of a typical field configuration. So in this classical limit, we'll get a classical field theory. And so you'll, in QFT1, you'll go in this direction. In this course, we're going to go in the other direction. We'll start with classical field theory and show that we can quantize it to get a quantum field theory. And we'll at times check that the quantum field theories we get obey the expected properties of quantum mechanics, special relativity, and locality. This backwards direction is much easier. The forward direction, in some sense, is more satisfying. You're starting from fundamental principles and trying to get to a quantum field theory. We'll discuss how it's gone. Yes.
This might be a very naive question. Why do we impose okay, maybe no. Maybe the question can be phrased as, because things like entanglement and stuff seems to have like action at a distance.
That's right. Yes, we of course want to allow for entanglement. What we really don't want is non-local propagation of information. That's a problem. We also don't want our field theories to have a strong dependence on the distant environment. What we should be able to describe physics locally using information about the laboratory. We shouldn't care what's going on in a distant galaxy. We shouldn't need that information. So you'll discuss these constraints more in QFT1, exactly what's meant by locality. But those are the it's not as strong a notion of locality as in classical physics that we're trying to demand. Yes.
Why should we think locality is separate from spatial relativity?
You could have a theory that obeys special relativity, but that's invariant under the symmetries of Minkowski space, but it's not local. Such theories exist. They're not very physical, but this alone doesn't forbid some pathological theories. Okay.
Sorry, could you repeat what you said about the classical limit? You said something about action over h bar. I just didn't hear.
Oh, if you're worried about taking a fundamental physical parameter to 0, mathematically it makes sense. Physically, it doesn't make so much sense. You can think about this limit in another way as, say, the action over h bar going to infinity, typical action. So you can find a limit where you're scaling your system so that the action grows and quantum effects become unimportant. Yes. Yeah, the classical limit is something we'll discuss much more in QFT2. We won't focus so much on it in this course. We'll start from here, go the other way. Okay. Okay. Yes. So so we're starting with a field theory, and we want to describe the interaction of particles. And what we're going to see very roughly is that particles are excitations of fields. So we can approach the problem we set out to at the beginning of the course, the scattering of particles, indirectly by introducing fields so that we maintain locality. Another reason to introduce fields is, well, we can try to construct a relativistic quantum theory without fields, and you'll do this in tutorial on Friday. And you'll see there are some pathologies. So the theory we'll look at on Friday is a single particle quantum system with a relativistic Hamiltonian. Hamiltonian will be p squared plus m squared. And when I draw this arrow symbol on top of a variable, this means this is a 3 vector. And this seems like a sensible theory. We can take single particle quantum mechanics, write down a relativistic Hamiltonian for it. And what we'll find, though, is rather surprising. We look at space-time diagram here, where the time is going in the vertical direction. Find that if we start a particle at the origin, and ask what's the amplitude for that particle to propagate to a space-like point here, which I'll call y, what we'll find is that the propagator and in particular the space-like propagator is non-zero. So if you just do the simplest thing you can imagine, take single particle quantum mechanics, change the Hamiltonian a bit. Well, you find faster than light propagation, which is problematic. So this doesn't work, and that's rather surprising. It fails. And the reason comes back to what I emphasized at the beginning, which is that when we want to combine quantum theory with special relativity, particle creation and annihilation is an essential part of the process. So here we're imposing a fixed particle number, and that doesn't work. And you can do a very similar calculation in quantum field theory and find that there's no problem. So we'll again briefly look at that in tutorial on Friday. Okay. Any questions on that? Oh.
These things are described by fields and aren't spatially localized, so they have like some sort of spatial extent. How do we exactly assign like a position to that and then calculate what will be slightly outside of it? Because I think like it would be a non-zero probability of measuring it slightly far away from even if it's space-like.
Yes, Cole, that's a very physical way to think about why this construction fails. Yeah, we'll make explicit the assumptions we're making here, and so we're making several assumptions that aren't really reasonable when we think about a relativistic quantum theory. One is fixed particle number, another is the existence of a position operator. I'll have more to say about that in a few minutes. And please don't forget, if you want to use the anonymous question board, feel free. Okay. Okay, so quantum field theory solves a number of mysteries that have no explanation in either special relativity or quantum mechanics alone, at least that I know of. One seemingly ubiquitous fact about our universe is that there exist identical particles. Every electron we have ever measured has exactly the same spin, exactly the same mass, exactly the same electric charge. That's just an assumption in non-relativistic quantum mechanics, but it has an extremely natural explanation in quantum field theory. So in quantum field theory, identical particles are identical because they're all excitations of a single field. Instead of postulating 10 to some large number of identical electrons throughout the universe, you just have to say that there's a single electron field everywhere, and all the electrons are identical because they're excitations of that one fundamental field. So this is it's a rather simple but deep fact about our universe, or explanation for why identical particles are identical. Another key mystery that is explained rather naturally by quantum field theory is the existence of antimatter. So this requires more explanation, and I won't give a full explanation here. This is something we'll look at in more detail later. One tool we're going to use to study quantum field theory are called Feynman diagrams. They're tools for describing the scattering process that we're trying to understand. And so I'll draw some Feynman diagrams here, and we'll look at more features of these and how we can use these to make quantitative predictions later. But for now, you can just think of them as space-time diagrams, roughly depicting possible histories of what happened in a scattering process. I'm being a little bit loose here, but we'll be more precise later. So let's look at a particular example. Let's suppose we're interested in the scattering of a proton with a neutron. So the two nucleons that make up nuclei of atoms. Proton's positively charged, neutron is neutral. Suppose we have a scattering experiment where we're going to scatter these. So I'm drawing them coming in from the asymptotic path. They're at the bottom of our diagram. And I'll assume that the final state is a neutron and a proton. Slightly revise my diagram. Okay. And one way we can complete this diagram is we can say that neutrons and protons scatter by exchanging a virtual particle. And protons and neutrons can exchange a virtual pion. This is another type of elementary particle or composite particle that's made up of quarks, just like neutrons and protons. Pions are made up of a quark and an antiquark. They're unstable. You don't see them as frequently at low energies as protons and neutrons. So Feynman diagrams, we can think. So they're both concrete calculational tools. We will later in the course assign complex numbers to each diagram. There's a process by which we can add up those complex numbers to predict amplitudes for scattering processes. We'll get into that later. For now, just think about this as a picture for a possible space-time history of what happens in a scattering process. That's a rough way of thinking about it, but gives you some useful motivation. So what happens in this picture is we have a proton and a neutron, which are propagating through space-time. Proton then at some time turns into a neutron and a pion. So particle splits. And sometime later, the pion is absorbed by the neutron and becomes a proton. For this to make sense, and also to conserve charge, the pion has to be positively charged. Now, if this is a valid diagram, the theory is going to be special relativistic. It's going to have the symmetries of Minkowski space. Can boost this diagram and get a valid diagram. So we do a boost. And these two space-time points, where the particle, these two space-time points x and y, where the pion is emitted and absorbed, are space-like. Then we can change the relative order of those by a boost. So let's look at this diagram in a boosted frame of reference. Boosted frame of reference. Y is first, x is second. And we still have a pion here. And we can look at what charge conservation tells us at either vertex. So if we look at this vertex, we have charge 0 going into the vertex, charge 1 leaving from the proton. So what should the charge for the pion be? Minus 1. Yes. So this has to be negatively charged. And so this is an example of an antiparticle. So the pi plus and pi minus are antiparticles of each other. They have identical properties except for opposite electric charge. So this again is a cruder argument than one we'll look at later in the course. But we'll see that if we look at quantum field theories that contain charged particles, those necessarily have both particles and antiparticles. That's a general feature of quantum field theory. Again, it's rather mysterious if you look at non-relativistic quantum mechanics or special relativity law. Okay. A third mystery that is solved by quantum field theory is the relationship between spin and statistics. So you all know that integer spin particles obey commutation relations, or Bose-Einstein statistics, and half integer spin particles have anti-commutators, or in other words, they obey Fermi-Dirac statistics. So that's just an assumption in non-relativistic quantum mechanics. There's a spin statistics theorem in quantum field theory that shows that under rather general conditions, any relativistic quantum theory has to have this feature, where spin and statistics are deeply connected. We won't discuss the proof of that theorem in this course, but I think you may touch on that in QFT 1. It's an important and deep result. Yes?
From STR, we know that cause will always precede effect.
Mm-hmm.
So here, if you look at the event X at point X, when pi plus is getting released,
mm-hmm.
is the cause for event at Y when the neutron is merging with pi plus. So can we say that there will be a frame where like event at Y is happening first and event at X?
So I'm assuming here that the X and Y are space-like. And whether this makes sense should be mysterious to you at this point. I claim it makes sense. That there are diagrams like this, and that if we account for all possible diagrams like this, we still end up with a theory that doesn't violate causality. Yeah, you're right to be skeptical. This is a claim that I haven't backed up yet, and we'll need to build up some additional tools to address why this makes sense.
So these pi particles are like space, like their velocity is space-like.
That's right. Yes. Yeah. You're absolutely right to be concerned. You should all be concerned if you. But this is the claim, is that these diagrams do contribute. We'll see why later. Yes. So important is that not just single diagrams like this, where we're integrating over classes or integrating over locations X and Y, and that integration is an important part of how the acausal features of individual diagrams cancel out. Yeah, we'll see that later. Okay, so an hour and a half is a very long time to focus, and I plan to take 5-minute breaks at about the halfway point. It won't exactly always be on the dot as today. It might be a little earlier or later, but let's resume in 5 minutes.
Yeah.
So our starting point is going to be a classical field theory, and we'll start discussing classical field theories in a few minutes. And And what we're going to do is quantize those classical field theories. There are two important methods for quantizing classical field theories, one of which we'll focus on in this course. So that's basically what we're going to do. Is we're going to take a field called phi and promote it to an operator. So this is very analogous to what you've done in non-relativistic quantum mechanics, where you take position and momentum and promote them to operators. This is one method of getting quantum field theory. There's another important method that you'll learn about in the Quantum Field Theory 2 course, and which will be used in a number of the elective courses as well, which is rather different. So you start with a classical field theory, and instead of promoting the field to an operator, instead integrate over all possible field configurations. This first method is known as canonical quantization. And it will be the focus of this course and QFT 1. This method has some advantages, one of which is the connection between fields and particles is much more clear in this using this method. We'll also see that we can rather more easily than in the other quantization method derive a number of important exact results in quantum field theory. Exact results are rather rare, and we'll discuss a number of those in the next few weeks. So the canonical quantization method makes easier to derive. The other method is known as path or functional integral quantization. Will be introduced in quantum field theory 2. It also there are a number of aspects are easier to see in the functional integral formalism. So both have their advantages. We'll learn one first, but this is not. I just want you to know from the outset that it's not the only way we can do quantum field theory. There are other equally powerful ways we'll look at later in the year. Okay. So given that we're going to use canonical quantization, we see one important question that arises right away, which is how to deal with position and time. And Colt alluded to this earlier. So in non-relativistic quantum mechanics, we treat position and time very differently. So in non-relativistic quantum mechanics, position is an operator. Time is a parameter. And if we want to construct a relativistic theory, it's not the best idea to start out with position and time treated in such drastically different ways. So there's two natural ways we could try to fix this. One is we could promote time to an operator. If we do that, a natural question is what do we use to describe what parameter do we use to describe the time evolution of the system? One answer is proper time. Could do that, but this answer is not unique. Could use any, not any, but any smooth monotonic function of proper time. So this is an increasing function that's continuous, derivative. Also use that to describe the evolution of our system. This works, can be done. It's rather complicated, but this is a variation of this is something we'll discuss in some of the elective courses later in the year. So if we do this, we can have a position and time operator that's a function of proper time. And if we have it, it's a function of proper time, there's no reason we couldn't add extra parameters to grab the evolution, and that's essentially what string theory does. We add another parameter. We get string theory. Where we will have position and time operators. So this formula can work, and you can develop quantum field theory along these lines. It's not nearly as straightforward as the method we're going to take. Yes, Sergey?
What does the second parameter signify?
So this is a spatial parameter. So these are coordinates along a 1 + 1 dimensional object. You can think of as a string that's, we can just describe a string by a world sheet. We need two parameters to describe it. One is the length along the string, and the other is the propagation through time. Okay, so the method we're going to take is the other method, is to demote position from an operator to a parameter. And so in our formulation of quantum field theory, we're not going to discuss a position operator. We don't have the same position operator that we do in quantum mechanics. You can construct something that sort of looks like it, but there's no position operator that has all the properties that you would want, that has the right commutation relations and the same relationship, or Fourier transform relationship with momentum basis. So doesn't quite work in you can construct something that approximately looks like what you'd expect for a position operator, but it doesn't have all the expected properties simultaneously. So we won't discuss that much. So we will not discuss position operator. So that's a rather important change from quantum mechanics. Don't have, at least in the same sense, position operator.
Sorry, yeah?
Yes, go ahead.
If QFT contains quantum mechanics, shouldn't the position of a particle, for example, be quantized? And if we demote the position operator to just a function, how do we implement the quantization in space? Like a finite set of eigenvalues are possible in quantum mechanics.
Yes.
If it's not an operator anymore.
So we won't never work in a position basis. We'll always work in a momentum basis. There's other useful bases that we can use in quantum field theory. You'll see. We'll get around this. And so in some sense, the non-existence of this position operator comes down to the problem of localizing exactly a particle in relativistic quantum mechanics. There's always going to be some uncertainty in the position of some Compton wavelength. And we can't, in the same sense, localize a particle in relativistic on relativistic quantum mechanics. Yeah. We can, yeah, the obstacles to constructing a position operator with all the expected properties goes away in the limit that C goes to infinity.
So does it equal to give up the uncertainty relation?
We're not giving up the uncertainty relation. We're just giving up the, or for the purpose of this class at least, we're giving up the position operator.
Is this two method completely identical? Like there should be some physical consequences and some differences between like treating time and space as operator or parameter. Like the first one, when you treat time as an operator, then it means that you're quantizing time as well as space as well. Like, I mean, are the predictions completely the same?
Completely the same. Yes, predictions. There's many ways to get quantum field theory and many different formulations of quantum field theory. We'll see. We're not going to discuss this formulation in any of the side classes, but we will discuss functional integral quantization. And you'll see that the formulation of quantum field theory looks drastically different in this formulation, but predictions are identical.
But treating time and space as operator or parameter, it doesn't have any physical consequences.
No, it's the same.
Why? Because you're not expanding anything in the position space basis. That's why it doesn't have consequences.
Yes.
Because the whole basis of moving from classical mechanics to quantum mechanics was to promote parameters to operators. But if you demote them back to parameters,
So that's the way we're.
an operator that you're working with. So that would be the momentum thing, the momentum parameter, right?
So the way we're working in this class. In this class, we're starting here. This is, in some sense, we're starting here essentially because it's easier, not because it makes more sense. Really, this is the fundamental theory, and it makes sense to take a limit of a fundamental theory to get a less fundamental theory, not the other way around. In fact, could have different quantum field theories that have the same classical limit. Not clear that going this way we get a unique theory, and in fact, we'll see that there's some ambiguities, at least in some cases. So quantization procedures are important to understand, but I don't think of them as fundamental. Really, this is what's fundamental, and these are tools we have to try to get at this. But it's also not clear that every quantum field theory can be constructed in this way. There may be quantum field theories that don't have quantum
Maybe I should rephrase my
classical
question.
limits.
If you before doing so, if you were to start by demoting the operators to parameters, would you have predicted that it wouldn't make any difference if you demoted them or you promoted the time to an operator? Could you have predicted that, or after doing all the calculations, you said, okay, they're basically the same thing?
So going from here to here, again, there's some ambiguity. It's not clear if you'll always end up at the same spot. Going backwards, it's clear. So maybe that it is surprising in a sense, because it's not necessarily clear that you can go backwards and invert this classical limit process in all cases, or when you can if you end up at the same spot, because it's certainly possible that multiple quantum field theories have the same classical limit. Okay. Before we briefly introduce some classical field theory, I just want to talk about one more general feature of quantum field theories we should keep in mind throughout the course. And question of what can we measure is an important thing to keep in mind throughout this course and when studying quantum field theory. So we know that any measurement we can do must give us a finite result. There must be we have a physical theory. It should give us a unique prediction, or at least a probabilistic prediction for what the result of the experiment should be. So if we have a physical theory, it should make predictions. Unique prediction, at least for the probability of making any given measurement. And those predictions should be finite. Often if we write down a physical theory, there's some unknown parameters in the theory. For example, we write down a physical theory describing a ball in a fixed gravitational field. There's two parameters: the strength of the gravitational field, the mass of the ball. Once we specify those, we're specifying the physical theory. We should be able to specify our physical theory by the results of some measurements we do at that system. That's usually not something we think about carefully when we're thinking about classical mechanics. We can measure almost any property of a classical theory. So we can specify a physical theory by some set of measurements. We might want to make the restriction that's a finite set of measurements. This is not, in many contexts, in classical physics or relativistic, in special relativity, or even quantum theory, this is not such an important constraint. You can specify these by measurements. You can measure many properties. And so if we specify a physical theory, we can make some predictions. In making those predictions, we might want to introduce some extra quantities that we use for our calculations that are not necessary to describe the physical theory or are not necessary for the predictions. For example, if we have our ball in a gravitational field, we might want to introduce a coordinate system. The origin of the coordinate system, or the height of the ball, is not relative to that coordinate system. Is something we can choose by choosing the origin of our coordinate system. So the location of that origin of the coordinate system is not physical. Nevertheless, it's useful. Something we want to do in intermediate steps in order to make a prediction. In most contexts you've come across, those intermediate calculational choices you made are finite. Doesn't have to be. Could choose my origin for the ball to be at minus infinity. Nothing's stopping me from doing that. So rather unnatural choice in that classical mechanics example. But in quantum field theory, that's not true. Many times our intermediate, at least the natural choice for our intermediate steps, not in our specification of the physical theory or in our predictions, will involve infinities. That's not a problem. They're just calculational tools that happen to involve infinities. That's important to keep in mind. We'll see infinities popping up all over the place in this course and future courses in quantum field theory. That does not say anything about whether the physical theories are finite or not, or whether our predictions are finite or not. These are just calculational tools. So infinities will pop up, but infinities in unobservable quantities are not a problem. We see an infinity means one of two things. Either it's not something we can observe, or we've made a mistake. So these will pop up. Don't be shocked. It's just like choosing a origin minus infinity. Doesn't affect our physical results. Doesn't affect our specification in physical theory. We will need to think more carefully about how we specify our physical theory. It's not going to be as straightforward. We need to specify our physical theory by specifying the result of some set of measurements. And so this, what I'm discussing here, is related to the subject of renormalization. Which in some treatments you see as ways of getting rid of these infinities, but they're never really there if you think about it this way. Our physical theory is finite, our measurements are finite, the way we specify physical theory is finite. Our calculational tools may involve some infinities and intermediate steps. Any questions on this? Yes, okay.
For normalization, shouldn't be thought of as a way to remove infinities. What is it, or how should it be thought of?
It's a way to relate measurements at one energy scale to measurements at another energy scale. That's the way I think about it. And that's so you're specifying your theory, specifying the results, measurements. We typically do that in quantum field theory by specifying results of a few possible things we could measure at one energy scale. Or all of our incoming particles, they have the same energy. And once we've specified that, we can make unique finite predictions for any other measurement we can do at other energy scales, at least within the range of validity of our theory. So our classical mechanics example of a ball in a fixed gravitational field, that's an approximation to some physical theory. That'll break down if the ball becomes too massive, and so that it exerts back reaction on the gravitational field. So, and quantum field theories, unlike many other physical theories, often tell us their own range of validity, which is a cool and unexpected feature of quantum field theory. Okay. So our starting point is going to be classical fields. And we'll focus entirely for this course on scalar fields. So what I mean by scalar field is it's a function that takes a value at each point in space and time. And I can also write this in another way. It's a function of space-time. So here, this is a x with no vector symbol on top is a 4 vector. And in anything typed, lecture notes or tutorials or quizzes, 4 vectors will be italic. Also in anything typed, 3 vectors, like x here, will be bold. That's our notation, with the exception of measures. So for measures, I'll indicate a 3 vector measure as d3x, d4x, and in neither case will they have a vector symbol on top, and they'll both be italic in that case. We are going to work with a Minkowski metric that is mostly negative. So what this means, I square the 4 vector x. That's equal to t squared minus x squared. This is the same convention we'll use in QFT1. In QFT2, we will switch. Yes. I'm sorry. Gotcha.
May I ask why? It's just like, are we going to use like a different textbook with different examples, or are we going to switch between QFT1 and QFT2?
So in QFT2, for a large part of the course, we're going to work in imaginary time, where we'll take t to be it, t to be some purely imaginary number, in which case then the Euclidean metric would be all negative if we started with this. This convention simplifies. In this course, it doesn't matter so much. In QFT1, Gong preferred to use this symbol, so that's why I'm introducing it now, partly because the equations for spinor fields, for spin half, the fields that give rise to spin half particles are simpler with this. You'll find half the textbooks use this convention and half use the other, so introducing both in these courses is useful for navigating the literature. So, okay, so this is a classical field we'll study. For the most part, we'll assume that this is a real function, a real scalar field. Occasionally, we'll deal with complex scalar fields, where this phi is a complex number at each point in space and time instead of a real number. And one way to think about classical fields, which is useful for remembering how the quantization procedure works or understanding what we should do, is that get some colored chalk. We can think about a scalar field at each point in space as being like a generalized coordinate of some like a generalized coordinate with some label at some time. So here, this is a generalized coordinate. And A is a label. So X is continuous. Often in in classical mechanics, the label is discrete, but otherwise these are very much the same things. We've got some variable, depends on a label, which evolves in time. And when we quantize the theory, we'll promote Q's to operators, and we'll do the same thing, not the phi's to operators, very much the same way. Okay, so the Lagrangian formulation of classical field theory or quantum field theory is useful because the Lorentz invariance is manifest if we work in the Lagrangian formulation. We can easily check if we've got a Lorentz invariant theory. If we start from a Lorentz invariant Lagrangian, we'll be guaranteed to end up with a Lorentz invariant theory. So the Lagrangian we'll consider will be of the form integral over Lagrangians will be integrals of Lagrangian densities. And we'll be interested in Lagrangian densities. They take the form. They're functions of the field, and the four derivative of the field. And so this is the Lagrangian. I can also write the action as the integral dt. So we're to write that. So here, this is the Lagrangian. Writing the Lagrangian as an integral over space of the Lagrangian density. And almost all the time, people call this Lagrangian, even though the integral of it's Lagrangian. So you will often hear me abuse notation in a slight but extremely common way of just calling this the Lagrangian. So we're going to consider Lagrangians of this form. So we're only allowing four derivatives of the Lagrangian to show up. And that's because we want to start with a Lorentz invariant theory. If we have time derivatives here, but no space derivatives, our theory is not going to be Lorentz invariant. So this dependence here is for Lorentz invariance. And our fields here, and the derivatives only depend on x. So here I've written this as a single integral, and that's for locality. There's more general things we could write down. It would be Lorentz invariant, but not local. For example, we could write down a theory with an action contains an integral over two spatial positions. Write a Lagrangian that depends on phi of x, phi of y. This theory could be Lorentz invariant, but certainly wouldn't be local if we allowed direct couplings between fields at different points. We're not going to allow something like this. So these are the types of theories we're going to consider. So the Lagrangian formulation is useful because it Lorentz invariance is manifest. On the other hand, if we want to promote a field to an operator, the same way we promoted our generalized position to an operator in quantum mechanics, the natural way to do that is in the Hamiltonian formulation. The time evolution of operators and states is determined by the Hamiltonian. So we'll often need to work in the Hamiltonian formulation as well. Gotcha?
Sorry, I missed what you were saying when I was writing. Can you just repeat one more time why we're not considering an action or Lagrangian with?
So an action of this form would have direct couplings between fields at different points in space-time, which would, in general, violate locality.
Oh, okay.
So you started with a theory like this, you could end up with a Lorentz invariant theory. It wouldn't be local, at least in general. Perhaps there can be some cancellation between the non-local effects, but in general, you started with a theory like this, in general, it would be non-local.
Why are we only considering phi to be a function of x and not also t?
So this here is a 4-vector.
Oh, okay.
There's no vector symbol.
Are there interesting physical theories where people try to derive things from the ground up without the assumption of locality, and do they get anywhere?
There's been some work, yes, on non-local theories. It's not an area that I'm an expert on, but if you're interested, I can try to help you navigate the literature. I know some people have done work on that.
Okay, thank you.
And so the Hamiltonian formulation has the advantages that it's natural for our quantization procedure, but it doesn't have this nice Lorentz invariance property. Yes, Mary?
Sorry, if we were on the metric that wasn't Minkowski, would the del of mu have to be the covariant derivatives? Like, does it translate like that? Like, if you want Lorentz invariance and then you want covariance? Or do we not really consider that?
So if we had a curve, many things would change if we're on a curved background. Yes. So that depending on what you want what restrictions you want to put on your theory, you most likely would want to replace it with a covariant derivative. But yeah, that's a rich subject that we will discuss in some of the elective courses, but not yet. So.
I'm still a bit confused about the difference between Lorentz invariance and locality.
Mm-hmm.
We have a theory like the second one that we crossed out where you're coupling degrees of freedom at x and y. I don't understand how that could possibly be Lorentz invariance as long as, for example, x and y could be just like separated. X could be outside the like cone of y, for example. In what sense can a theory like that be Lorentz?
A theory like this could be Lorentz invariant in that the action and perhaps all the observables could be invariant or covariant under boost for the Lorentz group more generally. Yes, so we will. So the Hamiltonian formulation is less useful for the specification of the theory or for calculations, but for quantizing a theory, the quantization procedure, this is the natural formulation to work in. We will work in that. The reason it's not, Lorentz invariance is not manifest is the Hamiltonian generates time translation. The Hamiltonian is deeply connected to the notion of time evolution in quantum mechanics. And so in order to specify a Hamiltonian, we need to pick a time coordinate, which is not a Lorentz, at least not a manifestly Lorentz invariant thing. So that's why Hamiltonian is not as natural a starting point as the Lagrangian. And our Hamiltonian is going to be defined in the same way as in particle mechanics. So the Hamiltonian in particle mechanics would be the E u dot minus L. We'll define it in the same way for in the field theory case. So in particle mechanics, we would find the conjugate momentum to some generalized coordinate as the derivative of the Lagrangian with respect to u dot. The analog of this equation for fields, so we define the conjugate momentum, pi, in general as a function of x, as the derivative of the Lagrangian. So here this is the, I really mean the Lagrangian, not the Lagrangian density with respect to pi dot. Sorry. It should be the Lagrangian. Yes, and so this is a time derivative here. This is what this is not a four derivative. This is a time derivative. So the Hamiltonian formulation treats time in a different way. Space. So over here, we do need to have 4 derivatives. Here we just have a time derivative.
Can you clarify why the 4 derivative is going to give us this Lorentz invariance, whereas a time derivative would not?
Well, so if we can look at an example. So an example action of this form could have integral b4x of y dot. That's the measure. So that's an action of this form if we allow it to depend on phi dot. And so the measure is manifestly Lorentz invariant. This has a time derivative, no space derivative, so this is manifestly. And yeah, so we're only allowing Lorentz invariant combinations of derivatives here. So this is manifestly not. This doesn't work. We would allow an action be a integral of d mu by also transforms under Lorentz transformations, but if we square it, right, d mu phi, then this is Lorentz invariant. We have got a Lorentz invariant combination. We won't discuss so much Lorentz invariance in this course. I'll be starting with Lorentz invariant Lagrangians. We'll consider explicit examples that have Lorentz invariant Lagrangians, and the Lorentz invariance of our quantum theories will be follow rather directly. This is a point you'll discuss in much more detail. There you'll look at fields that transform non-trivially under Lorentz transformations, and there'll be much more to say there. And you can basically for that reason, we're not going to focus on this so much. Okay. So next time we will look at a specific example of one of the simplest quantum field theories. We'll start with a classical field theory and then quantize it, and we'll see some surprising results. And in particular, this will show up next time. Thank you.